So we have a 10 kilogram block. It's initially at rest on frictionless surface, and it undergoes 3 types of forces. So the first force is a constant force of 20 newtons in the positive direction for 5 seconds. The second force is a constant 15 newtons for the next 3 seconds in the negative direction. And then the final force is some constant force being applied to it over 5 seconds. And if the block ends up where it started, we want to figure out what that final force is being applied to the block. So we're going to use essentially 2 things. We're going to use that the force equals the mass times the acceleration, and we're going to use these first 2 kinematic equations. We're going to break this up into sections, essentially just for the 3 types of motion and kind of bring them back to back. So for the first part of the motion, I'm essentially going to rearrange this equation to solve for the acceleration being the force over the mass of the block. And let's draw a little diagram here of what's going on essentially for the block. If it starts at, if we're looking at overall where it started, we can set up its initial start wherever. So we're just going to say, let's call this x naught, or x equals 0, essentially where it's going to start, and this will be our block. And it's going to travel left and maybe right because we have a negative force right here, and it's going to essentially we'll call to the right the positive direction and to the left the negative direction. And the forces are going to be applied to the block. It's going to move it, and then it's going to end up back where it started again. If it's frictionless, we're negating any frictional forces here, and since we know it's initially at rest, we know its initial velocity, at least for the first instance, to be 0 meters per second. So now that we have those parameters, we're going to use the first equation. So x final equals x initial plus v initial t plus 1/2 a, and this is the same t, right? So t squared. You can include delta t or just t since we know it's just a change. We're saying this one is over 5 seconds. We can just include that there. Now, if I denote that it's starting at the origin, I can say x naught is, or the x initial is x naught, which we can just say is 0 meters away from where it starts. We know that the initial velocity is 0, so then I can just simplify this equation to be x final equals 1/2. Instead of writing acceleration, I just denoted that acceleration is equal to force divided by mass. So I'm going to write that there. So it's going to be force over mass and the time squared. So this is going to get me my first displacement distance. And just as it undergoes that first force. Okay, so essentially we're going to set it up here. So I get x final equals 1/2. My first force is, it's going in the positive direction. So force is a vector. We're going to call that positive 20 newtons. And instead of writing newtons, I'm going to write its other unit, since we know 1 Newton is equal to 1 kilogram meter per second squared. The reason I do that is so you can see how all the units cancel. So it's 20 kilogram meter per second squared. All of that's then being divided by the 10 kilograms that the block, that's the block's mass, and then the second squared, which in this case is 5 seconds squared. So these seconds cancel with these seconds. The kilograms cancel with those kilograms. The only unit I have left is going to be meters. And then I get that the final distance of the block, 25 meters. I am also going to use the second kinematic equation. So v final equals v initial plus at to determine what is the velocity at which the block is traveling after it undergoes that first force. Okay. The reason for this is I'm going to need it when I set up the second set of, when I look at the second motion. So in this case, the initial velocity is still 0. I've also determined that my acceleration is the force divided by the mass. So this is then equal just to the force over the mass times the change in time, which in this case is going to be the 20 kilogram meter per second squared. I can write that properly. The mass, which is 10 kilograms, and the time, in this case, is going to be 5 seconds. One of these seconds cancels with this second. The kilograms cancel with this kilogram, so I'm left with a I'm left with a meters per second, which is the unit for velocity, so we're good there. Then I get that my final velocity is equal to 10 meters per second.
So to start the second type of motion, we have the second force, it's constant positive, so it's actually constant negative 15 newtons because it's going in the negative direction. And it's happening for 3 seconds. We can set it up for the second set of motion. Our initial velocity is our final velocity as before. So it's 10 meters per second. And our initial position is our final position from before. So our x initial is 25 meters. Everything else is the same setup. We use the same first kinematic equation. X final equals x initial plus v initial t plus 1/2. Instead of writing a, I'm going to write that the force is that the acceleration is equal to the force divided by the mass. So force divided by mass times the time squared. And I can't cancel any of the terms out, so none of them are 0. So this is my whole equation. I have the initial position being 25 meters plus 10 meters per second times the time, which is, in this case, 3 seconds for the second part of motion. And then plus 1/2. This is going to be my force, which in this case is negative 15 meters. I have the negative denoting it's going in the negative direction over 10 kilograms. Let me make sure I'm not missing anything. Yep. And then the time squared. So that's 3 seconds squared. This is, sorry, unit for force is kilogram meter per second squared. The seconds squared cancel, the kilograms cancel, these seconds cancel. I'm left with meter, meter, and a meter, and I'm looking for a meter.
X final, when I plug that all in, 8.25 meters. Now you might ask yourself, hey, if I have a negative this block, why all of a sudden why is it still traveling in the positive x direction, right? So because it's went from 25 meters to 48 meters, so it's still traveling in the positive direction, even though I've applied a negative force to it. And you can think of this negative force is slowing the block down, and if given enough time, the force would eventually stop the block and change its direction to the opposite direction. But there needs to be enough time for that force to be applied to the block in order for it to do so. So that's kind of why there's that discrepancy there. So either we increase the force or we give it enough time to stop it. And you can think of like if a car were rolling at you, assuming that it wouldn't crush you, right? So like let's say it's just rolling, it's not driving, or a big heavy boulder maybe, or a big heavy rock. Car's probably that example. But it would take a lot of force to even just get it to stop rolling before you could even change its direction. So it's the same principle as being applied here. So now let's look at just kind of setting up what that final velocity is. So the final velocity is equal to the initial velocity plus AT. It's coming from the second kinematic equation right here. And I can use this to determine exactly how fast it's going at the end of this motion. So that's going to be the initial velocity, which was the 10 meters per second. Plus, we know the acceleration was the force divided by the mass. That has not changed. This force, though, is going to be negative 15 kilogram meter per second squared over the 10 kilograms. The mass doesn't change. And the 3 seconds. When I plug everything in my calculator, I get that it is 5.5 meters per second, which, as we can see, it's still going in the positive direction, but it is slowing down. So now let's take a look at our final piece of motion, right? So now we have a constant force, but we don't know what that force is. We know, though, it's constant, it's being applied over 5 seconds, and the block ends up back where it starts. So that tells me my initial position, which was the position I started from the motion just directly before. So it's 48.25 meters. My final position is going to be 0 meters because I want it back where it starts. My initial velocity is going to be 5.5 meters per second, and the time that it takes to do so is 5 seconds. They give me that. And I'm going to use this to figure out my force. So we're going to use the first kinematic equation again. So x final equals x initial plus v initial delta t, or in this case we don't necessarily have to denote the delta, we just know it's t, So T plus 1/2. Instead of writing A, I'm going to write what A is. A is still the force divided by the mass. In this case, it's going to be the new force that we're applying for this third type of motion. So it's going to be the force over the mass times time squared. And I actually have everything in my equation to now rearrange this and solve for the force, because that's what I'm looking for. So we're going to rearrange this equation. We're going to subtract the initial position and the initial velocity from both sides of the equation. So we get x final minus x initial minus v initial t is equal to 1/2 the force over the mass times time squared. If I multiply t and m and divide by time squared, I can get force by itself. So the force is equal to Tm. I have x final minus x initial minus v initial t, all divided by t squared. So I'm going to plug in our values here. So we've got 2 times my mass, which is 10 kilograms. All multiplied by my final position, which is 0 meters, minus my initial position, which is 48.25 meters, minus my velocity, which is the 5.5 meters per second, times the amount of time it takes, so it's 5 seconds. All of that being multiplied to the 2 times 10 kilograms, and that's being divided by the 5 seconds squared. And if I plug that into my calculator, before we plug it in, let's check our units, right? So this second cancels with this second. I'm left with a meter times a kilogram, which if I want a force, I want newtons, and we know newtons is a kilogram meter per second squared. So those are the units I better have again. So I have a kilogram, I have times a meter, and then I have a second squared at the bottom. So it looks like we set this up right. And if we plug it into our calculator, we get negative 60.6 kilogram meter per second, or newtons.